Hi everyone, my name is Spencer Frank, and this is my tutorial on how to make a bridge structure in Abacus. So the bridge I have here is composed of three main parts, these towers, the rope, and the bridge deck itself. For the bridge deck and the towers, I've made those using 3D solid extrusions with these simple sketches here, and those are using solid homogeneous parts, and for the rope that's using a 3D wire sketch here, and that is assigned a beam section. The three materials I have here are oak, rope, and stone. I'll go over this very quickly, but I've assigned the three of those a mass density, so it'll work with a gravity load that I will be applying. In the properties section here, it's important to note that I've assigned an initial inertia value to these points here on the bridge. This is because when I was first attempting to run my model, I was getting a lot of solver errors involving zero mass, zero inertia, and even though I had the mass density specified, I realized a workaround to these solver errors is going up here to special inertia and creating an inertia value, a point mass inertia value on each of these points right here, and I just assign those a value of 1, 1, 1 for each direction, and the solver errors went away. Moving on to assembly, I've got several position constraints here, mostly just face-to-face constraints, and then these coincident points right here. Something I found really helpful when just making this assembly here is you can suppress some of these mates here, and this will allow you to apply various like connections and loads to these nodes specifically, and then resume the coincident relation. Moving on to the steps here, I've decided to do two different types of analysis, a dynamic analysis and a static analysis, and I have the raise and the lower steps here that are important for the dynamic analysis. Under interaction, I've specified a surface-to-surface contact between the bridge and the cables here. So in these interaction properties, for tangential behavior, I have rough friction, so that's no slip. There's going to be no slipping at these nodes here. Under normal behavior, I've got hard contact. And to connect these cables up to the bridge deck itself here, I've used connectors. I've experimented with using ties, using coupling, using MPC constraints, and I found really that using this connector feature here is the best way to connect everything up. So I've got 4 of those connectors in total, each of these nodes here at the end of the bridge. And this is the connector type I'm using. I'm using a beam connector for these connectors. I'll take a look at the mesh here. For the bridge deck itself, I've seeded the nodes like this, so there's 3 layers for the width of, or for the thickness of the bridge, so you can see the stresses in both of the outer layers and sort of like the neutral axis in the middle. For the rope, I've got basically just 50 beam elements here, and for the tower, this one doesn't play a super active role in the model, so it's a very simple mesh, but both the tower and the bridge deck itself are using these solid elements. Moving on to the loading. This is my static loading condition right here. So first of all, for the loads, I have gravity acting upon the cables, the ropes here, and the bridge deck itself, and negative 9.81 and the negative Z. And I found that applying gravity to these towers up here was giving me solver errors for some reason, so I've just got it applying to the bridge and the cables here. And now one of the most important boundary conditions in this model is this sort of bridge pivot at the end here. It's displacement, zero displacement in X, Y, and Z, but the rotation is unconstrained, so it can kind of raise and lower. For my static loading conditions here, I have fixed bridge end. This is just locking the end of the bridge here in the Z direction, so it can't raise and lower, kind of like if a drawbridge was in the lowered position, this would be like the ground that it's sitting on there. And then I have an encastre on the bottom surfaces of the towers here. And I'll go ahead and talk about this raised bridge end condition after I show you the first simulation here. So these are the results of the static simulation here, where there's this fixed end bridge condition. You can see that there's a lot of stress in the cables here, and it does deform a little bit due to the gravity load. It has a little bit of a, more of an arc here, and there is some stresses experienced in the center of the bridge here. And if I were to play the animation, this isn't intended to be a dynamic loading scenario, but you can see that the gravity is acting upon the cables. And now here's the real interesting part, the dynamic loading. So when I do my dynamic load, I'm going to unsuppress this raised bridge end right here. I'm going to resume it. And then this fixed bridge end here, I'm going to move right, so it's only going to apply on the last step here. And the effect I'm trying to create here is in the raised step, I have this raised bridge end boundary condition, which is a displacement boundary condition, which is going to raise the end of the bridge up here. And then in the lower step, I deactivate it and fix the end of the bridge, so the bridge kind of drops back down and gravity is being applied throughout this whole process, so it's basically just like a raise and a lower. I'm raising it up very slightly, 0.25 meters. I should mention all the dimensions for this part are in meters, kilograms, and newtons. So I've experimented with using like point loads to try and pull the end of this bridge up, but I found that it doesn't work very well. Also, and I found that the best way to get this end of the bridge to raise how I want it to for the purpose of this simulation is to give it a small displacement value here. So this is just going to raise the end of this up by 0.25 meters, and we'll see what that looks like. Alright, so we can see here, this is a little bit fast, but the end of the bridge is being raised and the cables are reacting to it. You can see that the end of this bridge is being raised up ever so slightly, and the cables are bending how we would expect them to bend. And there is some stress experienced in the cables and along the center of the bridge here. And yeah, that's about it. Thank you.